Dear students, good morning to all of you. I am Magesh Kumar, a faculty from Chemical Department, SRM IST. I welcome you all for this class. Now in this lecture, I would like to discuss an application of the design equation of a plug flow reactor, that is a PFR. So based on a problem in which data are given, so we would like to find the design variable for a plug flow reactor. See, let us to see how that design equation could be used here to find the volume of a reactor. So this problem is meant to find the volume of a plug flow reactor. So the statement of the problem is given here in simplified form. So which states that the reaction which we are dealing here is about the homogeneous gas decomposition of phosphine gas. So it's a decomposition reaction of phosphine. The stoichiometry for that reaction is also given here. Like 4 moles of phosphine gives us phosphorus vapor and then hydrogen gas. So this reaction, it proceeds at a temperature of 649 degrees Celsius and it is following the first order kinetics. So whose rate equation is given as minus RPH3 is equal to 10 per hour CPH3. Now this rate equation says that this 10 is the rate constant for the reaction. So it is the value of K, rate constant, because it is having the unit of per hour. Time inverse unit it is having. So this is supposed to be the rate constant value for the reaction. Now what size of PFR? So we have to calculate the size. Size means volume of the reactor. So volume of the PFR. PFR stands for plug flow reactor. So operating at 649 degrees Celsius and 460 kilopascal. So the temperature and the pressure values are given for the reaction. See now, out of this system, we will be achieving 80% conversion. So the fractional conversion of reactant A is to be achieved as 80%. So the feed is consisting of 40 moles of pure phosphine per hour. So the feed is not having any nut compound, it is like a pure feed. Only phosphine is entering into the reactor. So 40 moles of phosphine is entering per unit time or per hour basis. So this is the statement and the data that is available there in the problem also. See now with these data, let us to find the volume of reactor. That is size of reactor we have to calculate. Now before going to solve the problem, I would like to define some of the variables. For example, this I am doing it only for my convenience or for simplification purpose. So let A is equal to phosphine. So A is the component which indicates the phosphine. Like that, R indicates the phosphorus vapor and S indicates the hydrogen gas. So this I am defining for our convenience. For simplification, for representing the rate equation or the stoichiometry in a simpler manner. So if it is done like that, then the stoichiometry is modified in this form, like 4A, because we have taken the phosphine as component A, then the phosphorus as R, and then the hydrogen as S. So the given stoichiometry is rewritten in this format now, 4A giving us R plus 6S. Now this, since we are dealing with the plug flow reactor, so for PFR, the performance equation is V by FA0 is equal to integration Pxa by minus RA. So this V is the reactor volume, FA0 is the number of moles of A entering into the reactor per unit time, or it is called as the molar feed rate. So this value is given. Actually this FA0 value is given as 40 moles per hour. This FA0 value is given as 40 moles per hour. So 40 moles of pure phosphine is entering into the reactor per hour. So FA0 value is a given data. Now here this minus RA is the rate equation or reaction rate value. So this XA is the conversion achieved. That is also a given data, 80% conversion. That is equal to 0.8. So this minus RA rate equation is nothing but 10 into Ca, because here it is given as 10 per hour CPH3. Since we have considered the phosphine to be as the component A, so this is replaced with Ca. So this minus RA now it is rewritten as 10 Ca. Now from stoichiometry we find that 4 moles of A is giving us 7 moles of R. For example, left side we have 4 moles of the reactant, whereas right side we are having 1 plus 6, 7 moles of the product. That means 4 number of moles is giving us 7 moles of the product. So there is a change in number of moles. So which accounts for change in volume also. So it is a system is like a varying volume system. So for which the value of expansion factor is not equal to 0. So epsilon A is nothing but expansion factor. So which takes into account about the change in volume during the course of reaction. Okay. So now the expansion factor is not equal to 0. Like that, these data also are given in the problem statement itself. PA0 is the initial partial pressure of component A. That is equal to 460 kilopascal. So it is advisable to convert the unit into SI system of unit, like because everywhere kilopascal if it is given, better to convert the system, convert the unit into pascal. So 10 to the power of 3 pascal. So temperature also it is given in terms of centigrade. It is converted into Kelvin. So K value is 10 power inverse 1. So these are the initial data what we can able to correct from the given statement of the problem. With the equation is also defined now. Now let us to move on to the next step, that is the solution part. So the performance equation is substituted with the given informations. So V by Fa naught is equal to dxa divided by 10 Ca. So 10 Ca is the rate equation, that is the given data again. So conversion value is 0 to 0.8 because the lower limit for the conversion is 0. Starting point at time t equal to 0, nothing will be converted. That means Xa should be equal to 0. Upper limit is given. The design conversion value is 80%, so upper limit value should be 0.8. Now, for a varying volume system, this Ca is replaced with an equation of this form. So Ca is equal to Ca naught into 1 minus Xa divided by 1 plus epsilon A into Xa. So we have to include the expansion factor also when we calculate the Ca value for a system where the volume is changing with respect to the conversion. So the Ca is equal to Ca naught into 1 minus Xa divided by 1 plus epsilon A into Xa. So it is replaced with this entire square bracket term. Now, actually the variable for integration is Xa. So it is enough if we have that Xa variable on one side, and then see, let us write the other variables to the left hand side. For example, here this 10, this Ca naught, see all these terms are can be taken to the left hand side on cross multiplication. We are getting like this 10 Vca naught divided by Fa naught is equal to, now this entire function is inverted. So this term will come to numerator portion like this 1 plus epsilon A Xa, then this will be there denominator portion, that is 1 minus Xa into dxa will be there as it is. So now the function for integration is like this 1 plus epsilon A Xa divided by 1 minus Xa. Now let us to call it as equation number 1. See, if we have to find the value of integration separately, then use this equation 1 to calculate what is the V. V is the volume of reactor. But before going for finding the value of this integration, we need to calculate what is the expansion factor value also. That is a epsilon A value we have to get. So for that, I already explained you in the previous classes. We have to make some basis for calculation. Let me to say the basis what I have taken is 4 moles of the feed mixture. So with that basis, see, let us to move on to find the value for the expansion factor. Now we have to prepare a small table to find the to write all the component name and all, and then total number of moles when Xa equal to 0. Xa equal to 0 represent the 0% conversion condition, starting point of the reaction at time t equal to 0. Then Xa equal to 1 represent the 100% conversion. So the components included are whatever the components that are there, the stoichiometry, like A is there, then R is there, S is there. So all these 3 names I am mentioning here also. Okay, A, R, S, all these 3 component names are mentioned there. So by default, whether inert is there or not, always we have to include I also. This I represent the inert compound. This I represent the inert compound. So whether your feed is having inert or not, that is immaterial. Always it is better to include the inert also. If it is there, means mention the moles of inert present in the feed. If it is not there, we can take it as 0 also. Okay. Now here, initially we have 4 moles of A. That is the basis what we are considered here. So 4 moles of the feed mixture. Since our feed mixture is pure, that means that there is no presence of inert material. So inert is 0. Okay. So all the feed, whatever we have taken the basis, everything is made up of component A only. That is the conclusion what we can get. Okay. Now total number of moles of R should be equal to 0 because starting point there is no formation of R, as well as there is no formation of S also. So both R and S should be equal to 0. And also the I is equal to 0 because we are using pure A. We are using pure field. So pure field means no inert. So I should be, number of modes of inert should be equal to 0. Summing up all these things together, we get total number of modes as 4. That is at xa equal to 0, total number of modes of all the components put together is 0. Now at xa equal to 1, we have one more column also to be filled up. At xa equal to 1 means at 100% conversion, how many number of modes of each of the components are remaining in the system. That also we have to identify now. Xa equal to 1 means all the A would have become into product. That means no A is left out in the system. So number of modes of A is 0. 100% converted. Okay. Now total number of modes of R formed is it should be equal to 1 because stoichiometry says that